All right, so if you're in the right room, you're probably interested in understanding your apps or figuring out why they might not work as fast as you like. I'm Adrian. I've been working on an open source project called Zipkin for a couple of years. I work at Pivotal in the Spring Cloud group. And this is distributed tracing, so that if isn't a clear term for you now, hopefully it'll become more clear. And to jump into it, because we do have a time limit, unfortunately, latency is an interesting thing. It get kind of, people say it's like a product concern because we know if we have something take too long, we'll quickly find something else to do. And if we're trying to figure out sources of latency, there's a lot of tools that we can choose. So one of the things I did with this presentation recently is to rejig it to talk about like the different types of things we tend to use, which can help set in context what distributed tracing is and is not. And the nice thing is that regardless of what tools you're using, everything tends to be based on events. And so whether you're using logging or metrics or tracing or even some other things like error reporting, it's all derived from or it's creating new events. So like logging is the easiest thing. You know, our first programming assignment was to log hello world onto the screen. So we know that pretty well. We may still not do it too well, but we know how to do something with it. Metrics are interesting because it's taking events and then creating new ones, summarized data out of it. So for example, it might have a lot of recordings for response time, and then it creates a new one, which is an aggregate, like your max or your average or your P99. And tracing is events, so it's like requests coming through. But the neat thing about it is it helps you establish causality independently of time. So there's some neat things about these three tools. And they do have things in common, but they have a different focus in how they help us understand our systems. So logging, you know, we probably know logging's best at finding those exceptions we forgot to catch. And so logging is nice because it's a catch-all. It's also nice because it's stateless. Most of the time, one log message doesn't depend on another message to succeed. So it ends up being easy to program. But if you're trying to analyze it, it can be a little bit more tricky because your information does usually have some scoping to it. And so line by line, you might need some tools to sort of derive information out of it. Where logging and tracing overlap, one of the places is at request. So for example, if you have a web request, then you probably do have a log line related to it someplace. And tracing is usually request scoped. So for example, if you look at something we'll get into later, it will start with one entry point request in the system, and usually it's not like tracing GC, for example. So that's something that logging would do, but tracing doesn't do. So like you usually don't have a GC trace. Logging and tracing, you know, that they have request scope. Obviously, metrics can be about requests, and they usually are, like our response times and such like that. And tracing and metrics have some commonality because of the way that they're aggregated. So for example, if you aggregate traces, you can get a nice service graph. Like you can see how your services are communicating, and there's some neat things about that. But on the other hand, there's things that metrics and logging do which are different than like tracing. So for example, you may actually have metrics about like your time in GC, and that helps you with writing alerts and things. And so they're different tools and they have different focuses. And so I wanted to put this slide in here just to say that there is no like magic hammer and like all of a sudden, you know, tracing does everything for you. You have a lot of different tools, probably more than these, but they work together and they interact. And so it's kind of neat to think about where these overlaps are. And I was talking in generalization, but let's use something concrete like response time to compare them. So if you're lucky, you have a logging format for your HTTP logs that has something like response time already there. One thing I mentioned is that logs are relatively stateless. They should be stateless. But like in this format, you can actually see response time as a delimited field there. And this says that this request took 95 milliseconds. And that's nice because I don't actually have to like do math and like read one line and then see that this happened like 95 things after the other line. And so that's kind of helpful. We have some other metadata broken down about our user agent, which could be helpful when we're diagnosing things. Metrics also can show us response time, but it's more about like a population and like how your system is doing. So for example, whereas in a log it's talking about a single request and a single entry, and of course you have analysis tools to roll up classes of things. This is really where metrics shine. They can not only tell you whether or not 95 milliseconds was slow, but also whether it was slow in comparison with the rest of the system or other topics of interest. So like if you have a bad Amazon day, like maybe all of your system is slow, and so it's not very surprising that this request was slow. But if we look at this particular one in my ASCII art monitoring system, then I would find out that this was actually a bit slow of a request, even at the time that it occurred. However, if it had happened a bit earlier, then it would have been slow, but so were a lot of other things at the time. So metrics are neat because they give us a sense of like within our system how things are going, and that's something you can't get from just looking at a log. You can't tell if it's slow or not, and you need some more information to know that. And traces are really kind of a view of a request, and knowing that we're using microservices and things, they break down across different hosts, at least two. Like we always have like a web browser hitting a web server. So even if it's a very simple architecture, you have multiple hosts involved. And the thing that's nice about traces is like they can give you the why. So if you have a trace, like so for example, if we looked at this and we had the same 95 milliseconds here, we could see rule out causes or rule in explanations. So in this case, there was a wire send attempt, a redundant network transmission, that if that didn't happen, everything would have actually been quicker and would have been in our category of good requests. So if you're using a trace, the one thing that's nice is that you can give an answer pretty quickly and reasonably accurately. And when we're in a triage situation, it's pretty nice to be able to like give somebody the ability to say, okay, that's enough, let's move on. And so traces are kind of helpful for that. If you look at some of the nuances here too, like you can tell like the behavior of your app. Like so for example, this last command here outruns the critical path of the request, the async storage. So traces can also validate that your system is doing what you think it should be doing. So if you said that I have async storage, but it actually was still on the critical path, and guess what? You probably accidentally made it serial somehow. Anyway, so your thoughts are your own, but like I still like, I mean, everybody that I talk to isn't 100% in a situation where they never use logs. There's a lot of sites where tail minus F is the norm. And that's not bad. Like logs are useful. They're easy to get a hold of when you can't get a hold of other things. Metrics, however, their role is really to help give you trend information or like how your populations are doing. And of course, you can link these things together. So for example, within the scope that they exist, like a request scope, then you should be able to like pull up logs that have to do with the same request that's in the same trace. And so there's some things about that are useful. In distributed tracing, like what I think is nice about distributed tracing and what it does well is first off, it's a commoditization of knowledge. I think that's what tools that we sometimes say help us with observability. They're helping to explain something that's otherwise really difficult, if possible, to do. And like, for example, if somebody really knows their system well and it has a limited amount of components, they could probably guess or like manually track a request and where it's going from place to place. But these systems are trying to do this in near real time for you, so you don't have to be too smart. And if you have traces going on, you can actually use them not only to compare performance, but also to compare behavior, like the same application's behavior after it was upgraded to use a different component. And like everything, it has vocabulary involved, and I changed a slide today actually to add another thing because I noticed people were getting confused about the word instrumentation. So if I confuse you, then I've done the opposite of my intent. Span is the thing that we use in tracing a lot. It's basically span, like time span, and that's like the primary fact of an operation in tracing is how long it took. And it contains metadata around it as well, like tags, and I'll show you that later. A trace is where you take each of these operations and then you place them and model them like how they actually happen. So for example, this web request calls these 5 database requests. And so a trace would be those 6 things. And a tracer is usually referred to as the library that actually records things. And so if you're in metrics, you have like a gauge or something that you would put data into, and you get that from metrics registry. A tracer is a similar type of library, but for tracing. And instrumentation is that applied. So for example, if you are using, say JAX-RS or something like that, and there's instrumentation, trace instrumentation for JAX-RS, then when you look at your trace, you'd be able to see like perhaps the Java method that was mapped to that HTTP path. So instrumentation is actually what gives you detail on either a framework by framework basis or a service by service basis. So instrumentation is actually the thing that chooses what data will be in the trace. So if we look at span, this is the thing that pops up a lot. So this would be representing a command. If it's an HTTP, it has HTTP metadata around it. It will also have usually some sort of way to correlate what host or what node in the cluster it might have been in. And along with the time, you usually would also have some lookup keys like the request, and you'd have some things you can do comparisons with, like for example, a size. So the values vary, but always there's operation in some sort of a tagging, and sometimes there's events besides start and stop. And but at any rate, a span is mainly about one operation among the many that served your request. So tracing is like capturing these things as they occur. So if we had our other thing where we're having a post request and the tracing is a thing that's actually going through the system and connecting them. And while these recordings are going on, like when something happened, how long it took, the tracer doesn't actually decide what to do. It's just the library that's used to do it. Just like, for example, the database isn't the thing that is your business. You have business code that puts data in the database. So the tracer is just a tool, and it has the ability to do these things, but your instrumentation is actually doing the work. And the way that it works is usually there's 2 different directions of data in tracing. One is that there's propagation going on. So the only way that you can actually attach one request to another or one incoming message with a bunch of consumers of that message is if there's something propagated along with your request or along with your data such that you can tell accurately what caused what. Time isn't good enough because you can have a clock correction happen and then all of a sudden your trace is like negative time. Like you can't necessarily rely on time. You certainly, unless you're at Google, you can't do that across machines. So the way that it works is that there's IDs, and it's like a parent-child relationship. So I'm using symbols here just because I don't want people to get their mind anchored into numbers, because numbers don't matter. It's basically you have a parent, and say if its ID is star, then its direct child or children would have set its parent to star, and then they'd create their own, and then this would carry forward through this trace. And that's how the system can come back and regenerate the picture for you. So there's less coordination this way. So for example, everything can be sent asynchronously because each node knows exactly where its position is in the tree. And so when this data is collected, it's sent asynchronously, so there will probably be some sort of mechanism that is just going to wait for enough data and schlep it to the system. And so that's helpful because you want to do the least amount of work possible on your production request. You don't want to slow it down while you're observing it, and you don't want to give it new ways of crashing. So, yeah, great.
Why don't we just use this star?
Oh, because so the thing is that this is a pretty easy thing. You could just use one request ID through the system with something as simple as this. But if you have a number of things going concurrently, then when we think in Java, we might think about okay, this thread is doing this, and this thread is doing this, and this thread is doing this. So you need something secondary to sort of to resolve what happens to look at it happened at the same time because it's in parallel, and who actually caused what to occur. So in a very simple application, you won't necessarily see immediately the benefit of having operation-specific identifiers, but it generally will allow you to resolve things without using a clock to do it. And that's more important when there's multiple things going on at the same time. So yeah, just another, I'm going to say this a few times, but the thing that's doing the tracing is important. It's a mechanism, and the instrumentation is what and how it's done. So if you look at the code, one of the projects in Java I work on is called Brave, and it's a library, and it has a number of instrumentation for Kafka and all these other things. And even if something sounds similar, it can be very, very different how you hook into these libraries. So if you're using Apache HTTP client, if it's the async version versus a synchronous version, there will be different ways different techniques used to wrap these things. So instrumentation have a couple roles. One, they have to be expert of the libraries that they're observing, and they also need to know how to record data consistently, because when you're looking at something from an architecture point of view, you don't necessarily want to know that this was this library and this was that library. You really want to say, okay, these were HTTP requests going on. So on one hand, they're trying to do things in a generic fashion so that when they're displayed, they make sense and people don't have to know too much. So someone who's more focused on a database can still understand that this is a request and they don't have to know Java or Python. But on the other hand, they have to be experts at each library and know what they do. And so this is one of the things where I talk about commoditizing knowledge. If you have good trace instrumentation, then first off, you don't even know what's going on. And second off, the debugging is sort of automatic there. You'll be able to know when the network requests were sent and such. And so that helps you from having to manually do that with a debugger or log statements. And how it works out, let's just pretend we had a synchronous HTTP client. So it's invisible to the user because it would be another interceptor, like your logging interceptors or your authorization ones or what have you, right? So it's in the line of fire. It's going to do some steps like recording information and starting a timer, similar to how a metrics filter would work. And the thing that's very different about trace instrumentation versus something like metrics is that it does have to propagate state. It's a stateful system. So tracing by virtue of the fact that you need to reconnect everything, you do have to push the state of where you are in the graph for that to happen. And so it will actually add HTTP headers to the request, and so that the next side can see it. So this is how it basically works. And then when it's finished, sometime later, it will report the data. And the system that I'll be talking about this time, the usual time to read back is within a second or two. But depending on how your tracing system is set up, it could be minutes. So the instrumentation is deciding what to record and use the best approach possible to propagate that state. If you think about normal application management, performance management tools, they usually use agents to do this because you have all the tools possible. You have many ways of making things work. But trace instrumentation is not always done with agents. So for example, you can just configure an interceptor or have something like Spring Boot do that for you. And just a double underscore, this is your production request. So tracing is not something you just turn on in dev. It's something you have going all the time. And that has some impact. So the way that these tools are written are fairly careful, not just for adding overhead, but also not crashing your requests, because you should not care if the tracing system is down, for example. And so there's a lot of care taken, ideally, to make sure that this doesn't, you're not even aware that it's going on. And to deal with this, there are some policies and such to deal with the how much data is collected, how frequently. Usually it's probabilistic. So for example, 1% of requests would be traced, and the other ones would just have IDs in them, so you can use log correlation. And in the space of things that help you understand your system, the types of things that it does to help you with that are, one, taking these pieces and putting them into a single graph for you. And then the normal commodity functions like querying and visualization tools. Unlike things like logs, usually people don't store traces forever because it's quite large amount of data. So very, very frequently it's like days retention. Some people have it only for 2 days, and so they're just using it for very short term. They may have data that's derived from traces like dependency diagrams and things that would last longer, but the actual live data is usually short because of the volume of it. And yeah, we do tend to enter these discussions with latency, but most people, when they start using tracing, the first thing they do is if they're talking to me, they would say oh my God, my system is calling this, and I had no idea. And so it's really about understanding, and that's understanding your requests, understanding your architecture, what we think is going on is not always, especially when we're using different frameworks and layers and dynamic topologies and things. But you can also use it for other things that sound really hard to do, especially when we're encouraging microservices. So if you have quite a lot of things, you probably do have some sort of parts of your service graph that should be deprecated and should not be called. And knowing something's called and knowing why it's called are two different things. And so tracing can help you tell why it's called, because it might just be a mistake. And then the other thing I get a lot of feedback on is just this reduced time in triage, and that's one of the primary reasons people will look at tracing data. And Zipkin's a system that I've been working on for a couple of years. I didn't make the system. Johan Oxerson did back in 2012. It was created originally at Twitter to help with the fail whales, and so Zipkin is the name of a harpoon that will kill the fail whale. And it was based on Google's Dapper paper, and which preceded it by a couple of years, I think. And 2015, we actually created a independent community for Zipkin, which is still fostering it today. And it includes things that I've mentioned, and there's also technology that's not in our repo, and but anyway, it's a good place to start. The way that Zipkin architecture is usually described is to talk about this thing like your applications and whether they're instrumented or not. So for example, we don't have any way to record the internal details of MySQL, but we can record someone calling MySQL. So in some cases, you can have an instrumented client even though what you're calling is a black box. So for example, you might have a call to Amazon S3 and it currently is a black box, what happens inside S3. But these things are going to be interesting over the next few years because all the major cloud service providers are working on tracing solutions, which will allow you to see more and more information about like the cloud mechanics, as Alice from Dynatrace calls it. And the first I've seen of this type of work is in Amazon's Lambda service. So right now, if you know about these Lambdas, it's like you can execute a one-shot command based on some incoming message or just directly, and you'll be able to actually see a trace of what happened inside Amazon in preparation of that request. So that's kind of neat. So anyway, these apps, they collect data and they eventually schlep it onto some transport, by default HTTP, but it can also use Kafka and other things, and eventually get into Zipkin, which is a fairly simple architecture. It just stores and indexes things, and then it has a UI you can read. And it's originally it was tough to install, and then we kind of like took the bull by the horns on that, and so it can run as just a jar file, but we also even have like a kind of starter architecture for folks like MySQL, and it happens to be written in Spring Boot. Please don't create a custom server; you don't usually need one. But anyway, it's so you can download the jar and just spin it up. Now, sometimes people who are unfamiliar with tracing will say, "Oh, so I turned on Zipkin, and why don't I have any tracing stuff?" And the thing is that it's just a server, just like MySQL. If you start up MySQL, you don't have data in MySQL. You have to put the data in MySQL. And what it does is that the applications here, what we call instrumented. So there is some configuration at least needed on the application so that they'll be sending data to Zipkin. So you have to do something besides start the server. And I'll show a demo later. I can't see my time, so hopefully I'll have time to do that. We saw this, and I said, it looks easy, right? Well, you don't really want to write your own code unless you really like this as a hobbyist job, because there's lots of kind of interesting bugs that will wear you down. The most popular Java tracer was a library called Brave that was originally created by Christoph when he was at TomTom, and this is had a couple revisions, and there's some layered instrumentation out there that's not in the project for different types of frameworks. And the Spring Boot tracing, Spring Cloud Sleuth, this in this very recent like 2.0 version is actually itself a layer on top of it. So it's got lots of practice. One of the things that people at a Java conference they're interested in Java, right? But our architectures are made up with things that aren't always Java. So just because it's Jfokus, I'll talk about that, but obviously we have lots of different languages that our apps might be written in, and you don't want your architecture diagrams limited to just one language. So there's other types of tools out there. And there's some other types of open source tracing libraries. One that I'm particularly interested in is OpenCensus. This is the successor to Dapper at Google. They've started open sourcing this in a similar way that they did with gRPC. And its actually first customer is actually the gRPC. So if you're using tracing in gRPC, it's using this library. And as I said earlier, metrics and tracing and logging, this thing actually has nice ways of collecting both metrics and tracing together so that your querying across will be guaranteed to work. And it was originally made to support the Stackdriver cloud service offering that they have. And Stackdriver is actually a free service for tracing at least. But it also has plugins for Zipkin and things that compete with Zipkin like Jaeger. And there's also some other tools out there in the ecosystem. Open tracing is like an API definition. So it's basically like a Java interface. And so there's things that implement that interface, including in Zipkin. And there's a neat project that recently started, Apache Incubator Skywalking, which is a open source Java agent. So it will collect information. And one thing I like about this is it's primarily developed in China, and I like to encourage the non-Western world to make themselves known, because there's lots of things that are going on that are interesting that aren't necessarily described in English. So let's do a demo, huh? So I've got an app here, and in the OpenZipkin org, we have a bunch of apps that are like Dash examples. So if you just search for example, you'll find Ruby, Python, and things. And so this is a Spring Boot thing. So I have two Spring Boot applications here, front end and back end. And I do this because I don't want to try to like dazzle you with my like load balancing techniques, just to kind of let you know how things work in general. So in this, I'm using a REST template to just simply call the other service. And there's no tracing code here. So one of the things I was talking a lot about, like the mechanics and how things work with instrumentation, but actually in a decent environment, you'll never know. You just turn it on, you flip it on. You should question when you get into a situation where you feel like you're manually writing this stuff, because it's probably not a great idea. Anyway, so there's some conventions. So for example, if you name your Spring application, that will be the same name that shows up in Zipkin, but you can also override that and stuff. And the backend is just going to be printing a date and returning. And in this case, how is actually tracing enabled? Well, the first thing is we have a dependency. So this is using Cloud Starter Sleuth here. And then it's sending over Zipkin with the Zipkin thing. I have some other stuff here, which is interesting. Like most of the time, people want to do log correlation. So when Sleuth sets up, it can also like plop things into your logging pattern for you, so that even when something isn't going to Zipkin, you can still see what was associated with which IDs. So if I start up Zipkin here, let's see. So that's, like I said, it's a boot app in implementation. And it, by default, will store everything in memory. And it will actually throw out data. So please don't use this in production. But it won't OOM, or if it does, it's a bug. So it will just throw out stuff when you fill up. And so I'm going to start the apps here. And this part is not interesting. I'm just entering commands to start the Java processes. But and then I'm going to go ahead and invoke this with JavaScript that's also traced. So we have a library called Zipkin.js, and so in this case, I have browser.js here. And usually the pattern of tracing in implementation is wrapping something or intercepting something. And so this is taking the fetch library, which is like normal in JavaScript, and it's wrapping it with something that will trace it. But the actual command is just calling localhost and doing some nice promise transforms to put things on the console. Because that's why we do reactive, right? So if I open, that should have opened. Okay, maybe it went off the screen somewhere. Anyway, I'll just, so here's the I'm hitting the app server directly. And if I go to Zipkin, which is on port 9411, and and I look for any traces here, then I'll see that I hit it 3 times. And because whatever's going on here didn't work to bring up the JavaScript, maybe I can just, okay, cool. I'll hit it with JavaScript now. So if I find traces again, now I find that my browser was involved. So eventually, at the first time I was hitting it, I was just hitting the web app directly. And if I look at my dependency diagram, it now knows that this is part of my architecture. So Zipkin will create like arc diagrams for you. And for some people, that's really the only thing that they're interested in. They're like, but whatever. Anyhow, so we can tell some interesting things. We can make some guesses about what requests are slow and why. So for example, one of them was much slower than the others. And what was going on at the time. I'm sure we could figure out that some of this is just like starting the app for the first time. And then you would see like, requests that are having different performance. This is an interesting one where there's no child spans, right? So what happened here is because the browser, right? So it's using a pre-flight handler and using HTTP options to figure out like what methods are available. So sometimes when you're doing tracing, you try to like filter down what you're collecting so that you don't get a bunch of junk. Like maybe you accidentally trace like favicon.ico and you don't really care about favicon. So anyway, this is the tool, and it spits out things like this, and yeah. So you can if you had a real app, you could have hundreds of these. So it could look quite more interesting than this. So yeah, these are the 2 tools we're using, and they're all open source. And before, I actually have a fairly advanced section, so I'm going to preemptively give someone a chance to ask questions. And so I'll just go in here. So the thing is that under the covers, this stuff can be tricky because it's stateful. It's stateful because we have to know where we are in the position of the trace at all times. And it doesn't matter if you're using like RX Java or if you're using like a synchronous program, you need to always know where you are in this trace. And so the implicit responsibility is propagation, and that's one of the hardest parts of the implementation of tracing libraries and trace instrumentation. So not only are we talking about timing correctly, but we're talking about how to get this critical state moving around. From one side of the process to the other is very easy in synchronous architecture, but it's much more tricky if you're in an event loop and spinning around and doing weird things. Catching errors, making sure that they end up getting into the spans themselves so that you can see something that has actually gone wrong. So for example, if I were to go here and take out my back end, then I would expect that if I hit it again, I would see this, but also my trace data would have, see, I've got a red one there. So like your traces should be able to help you understand things, including errors that occurred. And like my favorite problem in all software is like our version woes. Like so we have what library is pinned to what thing and what thing, and so tracing, it has that too. Like you don't want your tracing library to interfere with your dependencies. So for example, our gRPC tracing library in Brave is actually using like Maven invoker tests to test the range all the way from 1.3 to 1.9 because like somebody's, we're passing deprecation cycles, so we have to be very careful how we do things. And I already talked about what instrumentation is. But the main thing is that there's 2 roles, like collecting data and also making sure the trace survives one side of the process to the other. And propagation is that part. So it's like this request scope state. When we're propagating in most Zipkin systems, and also some systems that aren't Zipkin, is using like headers that will say like B3 trace ID on them. And that's how other systems can read between processes where it was. And this part is the hardest part. It's the part that has the most bugs, the most leaks, the everything. Like, it's the most interesting and vexing part of working in tracing systems. And the reasons are, like that, for example, if you're working with thread pools and they grow, then they can implicitly inherit state. So you have to be really, really careful about these things. And also that, especially over the next couple of years, you're not going to be the only one. So one of the things I work on is a distributed tracing working group, so that when the cloud providers start having more tracing products, so that, in Amazon you can get information about your function invocation. That will also be the case in Google. And so you're not the only one. You may actually be in an environment where there's multiple graphs representing the same operation. So it gets really weird. But at the end of the day, the tools that are used, a scoping API, so something to place data and then clean it up when it's done, like try finally. And then techniques in the instrumentation. So for example, if you're in an asynchronous library, usually what's going on is it's like stashing something. You may have an attribute bag on like an eddy requests context, or you may literally have like a message ID that's incremented. And so there's some manual stuff sometimes going on. And where it gets hairy is because we have systems that are producer-consumer in basis, and like if you have a backlog and things start queuing, then usually that's also another new place that propagation can break. And the neat thing about that is that it breaks at the worst time, when you actually need the trace. So like when your system is actually overloaded and calls in haywire state, that's the type of place where all of these edge cases happen, and that's exactly when you need to know what's going on. So it's neat. If you don't have headers, then sometimes you have to like resort to envelopes. You may have done this with messaging. Like if you have some integration products, you may notice that they envelope things. But even headers seem neat, but like proxies will drop them, or some other service might rewrite it malformed for you. So it's just full of demons. And yeah, there's things that people don't tend to do what are possible. Like you can have libraries that interact with each other. But there's usually some coordination involved, so you have to have good relationships with them. Anyway, so that's geeky sidebar. But to wrap up, you don't have to go. I told you a lot of stuff about the details of tracing, and there's plenty more than what I mentioned. But that's just because this is a technical conference. Tracing is fairly simple to get started with. The demo that I showed you had really no code related to tracing involved. So I would say just play with it. Know that there's starter architecture, and a lot of the fancy stuff is available, and it will wait for you. So you can spin up your own environment pretty quickly with not a lot of cost. And there are other people who are working in these systems, and so you're not alone. So we have like a Gitter channel that's just about, I think, 1,000 people in that right now, and we have a Twitter feed that you can tell to find like when upgrades are going on and stuff. So if you're interested in this, I would invite you to join our community and try things out and let us know how it's going. And if you are interested in all of the demonic things that I mentioned, we have lots of backlog, and it's very interesting code to help with. So, but now over to question and answers. I got 5 minutes. So if you have anything you'd like to ask, and you can ask me anything, or if you want me to show you something, just go for it.
A question. Can you feed Zipkin with the data from Logstash or beats?
So the question is like, can you like post-process information and then schlep it in? Yeah. So some people, I know I've seen a project like for parsing like squid logs and things like that. So for example, the Brave API has the ability to record after the fact data, but we also have a separate project called like Reporter. And so as long as you can put it into the JSON format with the correct timestamps, then it'll be okay. A lot of people, like there's two storage backends that are very popular. Elasticsearch is one of them. And so we do have some people that are doing various types of things to get data in there that wasn't like instrumented at the time. Like as long as you parse logs and you can put it together, then you can. The things that you usually won't be able to do is tell like multiple hops, like parent-child relationships. But if you have one tier, like a proxy tier or something like that, it can be relatively straightforward. Other questions? All right, you let me off easy. Thanks for coming.